Welcome back. In this video, I would like to talk about the Kronig-Penney model. Before moving to that, let us discuss the wave function of electron in a periodic potential. Let's consider a periodic potential of this kind. U of x is equal to U of x plus A, where A is the periodicity of this potential or the periodicity of the lattice. The solution of wave equation for periodic potential of this kind was provided by Bloch. Okay, so let us discuss the Bloch theorem. Bloch proved that the solution of the Schrodinger equation for periodic potential must be of the form where uk of x is a function which has the same periodicity as the lattice. Therefore, you can say that uk of x plus a must be equal to uk of x. So this is a periodic function. So for a periodic potential, the wave function should be of this form. Okay. So the theorem we can explain in another word. Bloch theorem states that the eigenfunctions of the Schrodinger equation for a periodic potential are the product of a plane wave e raised to ikx and a function u of x with the periodicity of the crystal. This function psi of x is equal to uk of x e raised to I kx. The functions of this type are called Bloch functions. They are called Bloch function. So a periodic potential has a Schrodinger equation solution in the form of Bloch function. The function has an important property. Psi of x plus a. What is psi of x plus a then? This is nothing but u of x plus a e raised to I k into x plus a. Okay. So but we know this is periodic function, therefore this can be written as u of x e raised to, this can be expanded, u e raised to I kx into e raised to I k. Okay, this is nothing but psi of x into e raised to I k. Okay, so we can write this. So this is an important property of Bloch function. We will be using this property in our discussion of Kronig-Penney model. Now let us take the case of an electron in a periodic potential inside a crystal in one dimension. Okay, the simple model is called Kronig-Penney model. So let us explain the Kronig-Penney model here. Okay, Kronig and Penney assumed this potential as array of square well potential, which can be plotted like this. This is the periodic array of potentials, and the width of this potential barrier, these are the square well potentials. The width of the potential barrier is B, and the width of this well is A. So this is our 0 in x-axis. So this is x position, and this width is A, and this width is B. Therefore, this position is minus B. Okay, and this is A plus B. This is A plus B. This is A. This is 0. This is minus B. And in y-axis, we have potential, and the potential in the barrier is V equal to V0. So this potential is V0, and here the potential is V equal to 0. Okay, and at the boundary the potential is infinity. So this is the Kronig-Penney model. The potential is 0 in the region 1, and the potential V equal to V0 in the region 2. Okay. Now let us assume the electron is having an energy which is less than V0. So therefore we can write the Schrodinger equation of the electron in this periodic potential. Therefore, if m is the mass of electron, then we can write the Schrodinger equation. In region 1, the Schrodinger equation is given by minus h cross square by 2m p square psi by dx square is equal to E psi. You can write this thing as d square psi by dx square plus 2m by h cross square E psi is equal to 0. So this is the equation number 1. So we have one equation in the region 1. Here m is the mass of the electron, h cross, you know what is this is Planck constant, and psi is the function in the region 1. Okay, and in the region 2, that is in the barrier, that is the here the potential is V equal to 0. Here what is that? H cross square by 2m p square psi by dx square plus total energy. So this is kinetic energy, and the potential energy is V0 psi is equal to E psi. Therefore, we can rearrange this equation, that is p square psi by dx square plus 2m by h cross square E minus V0 psi is equal to 0. This is equation number 2. Okay. So we can substitute the value of 2m by h cross square E is equal to, so let's take 2m by h cross square E as some alpha square, or alpha is equal to, for alpha equal to root of 2m E by h cross square. Similarly, in this second equation, that here E is less than V0. So 2m V0 minus E by h cross square is equal to beta square. Okay. So substituting these two values in the equation 1 and 2, therefore equation 1 will become p square psi by dx square plus alpha square psi is equal to 0. This is equation number 3, and equation number 2 become d square psi by dx square minus, see here 2m by h cross square E minus V0 psi. So this will become minus beta square psi is equal to 0. This is equation number 4. So we have two equations. one in the region 1 and the second is in the region 2. Using the Bloch theorem, for a periodic potential, the solution of Schrodinger equation would be of this form: psi of x is equal to psi k of x is equal to u k of x e raised to I k x. So this is the solution of Schrodinger equation, a periodic potential, by Bloch theorem. You can write this equation number 5. Okay, we should use this wave function in this equation 3 and 4. So what is d square psi by dx square? For that we can find out first d psi by dx is equal to ik uk of x e raised to ikx plus du k by dx e raised to ikx. This is d psi by dx. Now d square psi by dx square is equal to ik square uk of x e raised to ikx plus ik du by dx e raised to ikx plus ik du by dx e raised to ikx plus d square u by dx square e raised to ikx, or this is equal to I square is minus 1, so minus k square uk plus, so e raised to ikx is that, let us take this as common to all this term, so ik du by dx, here also ik du by dx, so this is 2 ik du by dx, then plus d square by dx square, okay, e raised to ikx. Okay. Substituting this in this equation number 3, you can write equation number 3. Therefore, equation number 3 will become, let me write this equation first, this term first, d square u by dx square plus 2ik du by dx minus k square u minus k square u k square u e raised to ikx plus alpha square uk e raised to ikx is equal to 0. Okay, this can be simplified like this: d square u by dx square plus 2ik du by dx plus alpha square minus k square u e raised to ikx is equal to 0. Okay, so if this equation is true, then this bracket term must be 0. Therefore, d square u by dx square plus 2ik du by dx plus psi square, sorry, alpha square minus k square u is equal to 0. So this is equation number 6. U is the function, u is ufx. Okay, here we can write the characteristic equation as m square plus 2ik m plus alpha square minus k square is equal to 0. So this is the method in solving a differential equation, second order differential equation. Therefore, m is the root of this equation is m is equal to minus 2ik plus or minus root of b square minus 4ac. B square is 2ik whole square. So this will become minus 4k square minus 4 alpha square minus k square all divided by 2a. So 2. This can be written as minus 2ik plus or minus 2I alpha. Okay, divided by 2. Or we can have two equations. M is equal to minus ik plus or minus I alpha. Okay. So the general solution of this equation is, the general solution of the above equation 6 is u is equal to, so this is in the region 1, so we put this equation in this equation u1, this is d square u1 by dx, and this also alpha square minus k square u1 is equal to 0. Therefore u1 is equal to 0 because this function in the region 1, u1 is equal to a e raised to m1 x plus b e raised to m2 x. This is equal to a e raised to, first solution is minus ik plus I alpha. So therefore we can write I into alpha minus k x plus b e raised to minus alpha plus k minus I into alpha plus k into x. So this is the solution of the equation in region 1. Okay, so this equation number 7. Now substituting the value of d square psi by dx square in equation number 4, then what happens? D square u2 divided by dx square plus 2ik du2 by dx minus beta square minus k square psi. So therefore minus of beta square plus k square u2 is equal to 0. Okay. So we get the final equation as like this, similar to the equation 6. So we have this is equation number 8. But for the characteristic equation, m square plus 2ikm minus beta square plus k square minus of beta square plus k square is equal to 0. Therefore m, the solution of this quadratic equation, m is equal to minus 2ik plus or minus root of minus 4k square plus 4 into beta square plus k square divided by 2. The solutions are minus 2ik plus or minus 2 beta divided by 2, which is given by minus ik plus or minus beta. These are the solutions m1 and m2. Therefore the general solution of this equation is okay. So this is equation number 9. So we have equation 7 and equation 9. Here C and D are constants. So we have 4 constants A, B, C and D. So once you know what is U1 and U2, we can write psi is equal to U of x e raised to I kx. When U1 and U2 are wave functions, then this must be continuous. U1 and U2 must be continuous and periodic. Okay, so we can apply the boundary conditions. Here u1 is the solution in the region 1 and u2 is the solution in the region 2. So here once more I can draw u1 and so this is region 1 and this is region 2. So in this region this is 0 a minus b. In the first region u1 is the solution, u2 is the solution in the second region. They must be continuous if they are wave functions. Therefore u1 of 0 should be equal to u2 of 0. Okay, they are continuous. Here in the boundary, at the boundary they are continuous. Therefore we get u1 of 0. So the equation number 7, u1 of 0 means when x is equal to 0, what will be the equation? Equation 7 becomes a plus b. Okay, when x is equal to 0, a plus b is equal to u2 of 0. u2 of 0 is when x is equal to 0, this will become e raised to 0 c plus d. So u2 is equal to c plus d. This is equation number next equation number 10. So we have equation number 10, and next is the not only this thing du1 by dx and du2 by dx, the derivative of the wave function also continuous. So therefore du1 of x divided by dx at the boundary, that is at x equal to 0, is equal to du2 by dx at x equal to 0, must be continuous. Okay, therefore from equation 7, when we differentiate this thing, u1 du1 by dx is equal to a I alpha minus k into e raised to I alpha minus k x. Okay, I alpha minus k a e raised to I alpha minus k x minus I alpha plus k e raised to minus alpha plus k x into b is there. Okay, which is this is du1 by dx. du2 by dx is equal to, from equation 9, du2 by dx is beta minus ik c e raised to beta minus ik x minus beta plus ik e raised to d e raised to minus beta plus ik x. So these are du1 by dx and du2 by dx. So first we have to differentiate, and this should be continuous at the boundary. So therefore in this equation, applying in the equation number 11, this will be equal to, we get another equation. You can put this equation number as equation Roman 1. Okay, this is equation number 10, and equation number 10 become I alpha minus k a when x is equal to 0. This will be e raised to 0 minus I alpha plus k into b is equal to beta minus ik c minus beta plus ik into d. So we have another equation. This is equation Roman number 2. Equation number 2. This is equation number 1. So we have two equations. Now next boundary condition is periodic boundary condition, that is u1 of a is equal to u2 of minus b. Okay, so minus b. So here the periodicity is a plus b. A plus b is the periodicity, okay, of the crystal or the potential. Therefore, at what is the wave function at minus b? That is the wave function at a. Psi of a equal to psi of minus b, or u1 of a is equal to u2 of minus b. Therefore, using equation 7 and 9, you can write u1 of a is a e raised to I alpha minus k a plus b e raised to minus alpha plus k a is equal to u2 of minus b. So this will be c e raised to beta minus ik into minus b. So plus d e raised to minus of beta plus ik into minus b. So it will be plus beta plus ik into b. This is equation number 3. Next boundary condition is the derivative of u1 and u2 are also periodic. That means du1 by dx that is equal to a is equal to du2 divided by dx at x is equal to minus b. Using equation 7 and 9 again, we get du1 by dx a I alpha minus k into e raised to I alpha minus k a minus b I alpha plus k a raised to minus alpha plus k a is equal to c beta minus ik a raised to minus beta minus ik and b minus d beta plus ik a raised to minus beta plus ik into minus b. So it will be plus beta ik into b. Okay, so this is equation number. So we have 4 equations in A, B, C and D. So these equations will have non-vanishing solutions only if the determinant of the coefficients A, B, C and D vanishes. The determinant of the coefficients, the first equation is A plus B equal to C plus D, or we can write A plus B minus C minus D equal to 0. So like that in all these equations we can do that. Okay, so in the first equation the coefficients are 1 1 1 1. Okay, next equation, equation number 2, coefficients are I alpha minus k. Next is minus I alpha plus k beta minus ik minus of beta plus ik. Next coefficients are e raised to I alpha minus k a e raised to minus I alpha plus k a e raised to beta minus ik into minus b e raised to beta plus ik into b. The coefficients in the last equation are I alpha minus k e raised to I alpha minus k a minus I alpha minus plus k alpha plus k e raised to minus I alpha plus k a beta minus ik e raised to minus of beta minus ik b minus of beta plus ik e raised to beta plus ik b. Okay, so this is the determinant. This determinant must be 0 to have non-vanishing solution for all these 4 equations. Actually there are negative signs in the third and fourth columns, but it does not change the value of the determinant because it is 0. So, even if it is not 0, if we take out negative signs from two columns, it will be, the determinant will be invariant. Okay, if we solve this determinant, we can solve this determinant, 4 by 4 determinant. So if we solve this determinant, it will be we will get final expression as beta square minus alpha square by 2 alpha beta sine alpha a sine h beta b, hyperbolic sine function, plus cos alpha a cos h beta b is equal to cos k a plus b. So this is the final expression. If we solve this thing, all other terms will get cancelled. So this is the thing. Okay, this is enough for today. We will explain this equation in the next class. We'll continue our discussion of Kronig-Penney model in the next class.